Okay, folks. So, as promised, we're going to go over the Chapter 13 homework. We'll start Chapter 14 on Monday. The first test is over the IR and NMR and Mass Spec, as well as Chapter 13 and 14. We'll give you any chances to ask any questions you may have over any of those chapters when we get back before we start into Chapter 14, but here we go. We'll see how long it takes me to show you how to do this homework. Alright, got this loaded up and ready. Chapter 13. Arrange these in order of stability. So remember, primary, secondary, tertiary, allylic. Primary, secondary, tertiary, allylic. Allylic is the conjugated radical. The one we didn't talk about is one that involves a double bond, sp2 hybridized. That one is not really stable at all. So it'd much rather attack, the reason why we didn't even have to talk about that, it'd much rather attack the double bond than it would attack the hydrogen near a double bond. So it always would rather attack and bind to the pi cloud than it would extract a hydrogen. So we never even had to discuss that one. So C is the lowest. But so B is a primary. D is example of just a secondary. And A over here is allylic. It's in this case, a secondary that is conjugated with that. You can conjugate it with that double bond. Okay, let's see. Okay, let's see. They're telling me that C is higher than all of these. Oh my god, I'm such an idiot. Does anyone know why I got that wrong? It's because B, despite being primary, is also conjugated. So let's see if we know. B, despite being primary, is also conjugated. So let's do this one. Let's look. You got a primary, you got a secondary, you got a tertiary but allylic, you got that same situation, and then we got a secondary but allylic. So in terms of stability, D, A, B, then E, C. So my problem was that the primary ended up also being allylic. So if you have to compare a allylic secondary versus a allylic primary, the allylic secondary is better than the allylic primary, or allylic tertiary is better than the allylic secondary, the resonating one. So, draw the most stable radical that can result from a CH bond cleavage. So let's start by drawing my structure. Always I just redraw my structure, and then I can put in a radical. So, okay, remember, no rearrangement is allowed. So we got a primary, secondary, tertiary, and then secondary all the way around. Remember, unless it's a quaternary carbon, it has a hydrogen that it can lose. So the tertiary is always the most stable one unless we have some sort of double bond setup. See if I have another one. So this one, I'll do another one. So remember, we're only cleaving CH bonds. If you're going based on, well, this guy would be the most stable. Wouldn't a quaternary be better than a tertiary? Well, sure, if you could do that, but you couldn't do that without losing a methyl group, or we're only allowed to cleave CH bonds. So primary, 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 no CH bonds. Tertiary, secondary, all the way around. So even though they're quaternary carbon, quaternaries do not count because we're not cleaving the CC bonds. We're only cleaving the CH. Which alkyl halide can be prepared in good yields, radical halogenation of an alkane. So let's think about that. We're cleaving a CH bond and then adding that. So if I have 1, 2, 3, 4, we're looking at the original structure without the bromine. So that would be attacking at a secondary position, attacking at a primary position. This would be attacking at a tertiary position. So which would be the most stable and easiest to form? Tertiary all the way. Especially with bromine. If it was chlorine, you're going to get a mixture of all of them. However, you would still prefer the tertiary position. So primary, secondary, tertiary. You'll probably get more of the tertiary than you will of the secondary and primary. Okay, bromine. Here's the thing. Radical. It's not going to want to attack the ring. We're not going to want to attack the ring. So we have a secondary position and a primary position. Which one is going to be the most stable? Well, the secondary, of course, but there's another reason why the secondary position is going to be the most stable. That's because if I put a radical here, it can conjugate into this ring. So in terms of that, you're going to brominate the secondary spot. Now select, how would you do that? How would we turn the bromination into an alkene? We would probably want something to do with elimination. Elimination, the easiest way to do elimination is with a base. Strong, bulky base, ideally. So, tertiary butoxide. Butoxide is how you can make that. Let's see what another example might give us. So in this case, not halogenated. Oh, sorry, not no aromatic. So primary, tertiary, secondary, secondary. So where we're going to add to here. How would we get the alkene? Remember, Lindlar's gets rid of double bonds, but actually only get rid of triple bonds. Sodium hydroxide, you might be able to do it, but let's see, I'm trying to think of hydroxide might work. Not, yeah, it worked. So Now, okay, draw the mechanism for initiation. This is the hardest problem. Draw the mechanism for these 3 steps. Please note, almost always we're going to use this half-headed arrow. And in these half-headed arrow problems, we will need 2 of them. So I'm going to draw 1 half-headed arrow go into that atom, 1 half-headed arrow go into that atom. So it's splitting apart. Copy this down. I'm going to delete this bond between them and add a radical to each. So you will almost always needed 2 half-headed arrows. So now one of the things they leave off here is we're going to draw hydrogens to extract. Before we draw any hydrogens to extract, we need to figure out where we need to draw the hydrogens. Primary position, secondary position, tertiary, primary, primary. Where is the preferential loss? At the tertiary position. So what I'm going to do, in this case, I'm going to need 3 arrows. I'm going to just put this in space. They meet together in space, and I have to draw this arrow going to here. Now, with that in mind, I'm copying this molecule. I'm deleting this bond. Put in a radical there. And now I can draw. I don't need the HBr, but I'm going to put it in there just to show it. And I'm going to draw a second Br2. Br. And I'm going to put the... And now we're going to propagate. So once again, we need 3 arrows. One's going to here. One of these is going to meet in space. And one of those is going to meet in space. And then I just got to show, oh, hey, what did we do? We show a product. So I'm going to copy, once again, copy this molecule down. Except now I'm going to replace the H with my Br and I'm going to need a Br radical. And there's the propagation. I've propagated this. I've taken a radical, generated the radical alkane, and then I brominated, generating a new radical. So note, the 2 radicals are meeting in space. Do not draw the arrow, the half arrows, to the atom. Do not draw the half arrows to the atom. They just need to meet somewhere in space. Finally, show the termination of 2 alkyl radicals. So we're going to say these guys bump into each other. They bump into each other in space. So what will this look like? The easiest way to do this is, let's copy my structure twice. Copy that over. Oh, nope. Control C. Crap. I got rid of that arrow. I didn't want to do that. Okay. Copy this over. Now, I'm going to delete my radicals. And what has happened? I have made a bond between this atom and this atom. So I just have to draw this ridiculous looking bond. Now I'm going to pretty it up so you can see it better. But this is what it looks like. Here, I'm going to actually try to select and pretty it up. Okay, no, select. I want to select this guy. I'm going to pretty it up. just so it looks a little bit prettier. But this is what it essentially looks like. Oh crap. I just deleted one of my bonds accidentally. In my desire to pretty it up. I did not have to pretty this up. I just wanted you to be able to see what this kind of looks like. I just combined these two things together. It could have been as hideous as I had left it. That's the beauty of Alex. You don't have to have it pretty. I just wanted you to see what it would look like as a true molecule. But so, when you're meeting in space, literally what you're doing is you're just making a new bond between those two radicals. A new bond between those two radicals as they meet in space. This is a tricky looking problem, but if you work a couple of these out, it is rather easy. But remember, that first step, 2 arrows. Every other step, when you're generating 2 radicals, you get 2 arrows. When you're keeping one radical always present, you have 3. And when you're getting rid of 2 radicals, you only need 2 arrows. But the propagation step, 3 half arrows. The initiation and termination, 2 arrows. One of the monochlorination products of photochemical chlorination of 2-methylbutane is a tertiary alkyl chloride. Draw the structure. So let's draw my starting structure and then figure out where this. So there's my starting structure. It's a tertiary alkyl chloride. Where would a tertiary position be? Oh, right there. You'd be forming a chlorine at the tertiary carbon. Product 1 can then undergo dechlorination via E2, giving 2 alkene products. Provide the structures of these eliminations. So, drawing my starting material again, because we're losing the chlorine and we're losing a hydrogen. We could form an alkene there, losing a hydrogen there. I could also lose an alkene here. The major product is going to be here, the most substituted alkene. The minor product would be the least substituted alkene, but you would still get a mixture of the two. So we cannot avoid that. So read there, tertiary alkyl chloride. Tertiary alkyl chloride, we have a chlorine on a tertiary carbon. Looking at this, draw the structural of all organic products, including the stereochemistry, of the monochlorination. Consider only attacks at the C1 and C2 only. Hydrogens and the chiral carbons should not be included. So we don't want to include, so we have, let's draw my structure. Wedge. Now, there's a, when I attack with a chlorine, I can attack, we're saying C1 or C2. C1 or C2. Well, if I attack C1, now I'm not sure that's going to be super spontaneous, but if you do that, that's what you would get. Now, I'm gonna, can I copy? Yeah, I can copy. I'm gonna copy this down. If I attack the C2, delete that again. If I attack the C2, it is going to go square planar. So that means we could add the chloride to the top or to the bottom. And so you're going to get both the cis and the trans chloride. Now, I'm not quite so sure about the 1-1 substituted, but I know we would get the cis and the trans. But so because it goes square planar. Now, because if this one goes square planar, it doesn't really matter. Since they're both chlorides, it wouldn't really matter which one's chloride, which the chloride adds. Now, stereochemistry. Oh, okay, looking at this. What is the stereochemistry here? So chlorine is the heaviest, so that gets 1. C2 is the second heaviest, so that's going to give 2. And C6 over here is going to be 3. Now, unfortunately, the chlorine is away. While normally we would be traveling in a clockwise direction, going 1, 2, 3, but because it is away, we have to flip it. So C1 is on a S. Now C2, from C2's perspective, C1 is the heaviest, C3 followed by the methyl. So 1, 2, 3 with the hydrogen being away. So this is also S. And though the stereochemistry swaps around because we suddenly have the chlorine is now the heaviest on that atom, so stereochemistry is going to be totally different. Design a 2-step synthesis of 3-bromo, 5-methyl, 1-hexene from 5-methyl, 1-hexanol. Draw a precursor. So, okay. So, how many carbons do we have? 1, 2, 3, 4, 5, substitute out the 5, and 6. 1, 2, 3, 4, 5, substitute on the 5, and 6. So the first is, and it says disregard stereochemistry and competing products. So what's the first thing we notice? In our desired product, we have a bromine and we have an alkene. The easiest thing to do would be, and that alcohol is not going to be reacting with our halogenation. So the first thing we can do is dehydrate to make an alkene. So 1, 2, 3, 4, 5, substitute on the 5, 6, make that alkene. So once we have that alkene, we can do that. We can do it with sulfuric acid, or I think sulfuric acid would be the easiest method with heat to make the alkene. Now, brominate, we want to brominate at the, and we want to make sure it adds only at the allylic position. So we need something that's going to make sure it doesn't add across the double bond. We want to make sure it's something that is very mild, very, very mild. So our very mild thing is NBS. Our mildest radical mechanism is NBS. So let's try another one of these. So looking at this, we have a 4-carbon tertiary alcohol. Goes into a 4-carbon, actually, sorry, it's not 4-carbon. Yeah, it's 4-carbon. 1, 2, 3. A 4-carbon alkene. Same thing. We're going to form an alkene first. And then we're going to just, in this case, same thing, same steps. We don't want to add across the double bond, so we don't use HBr. We don't want to do BR-BR. So let's look. We got only a few more. NBS. Remember, NBS only adds to the allylic position. So step one is I'm drawing my starting material. NBS is going to add bromine right there. Now, hydroxide plus heat and water. I'm not sure if it's going to make an alcohol there. So I'm going to draw, oh, for God's sake. I wish I had my good mouse already attached, but I'm gonna, ugly. Let's see. Or it's either going to do an alcohol there, or with the base and heat, it might, I think instead, with the base and heat, I'm thinking instead, there's a good chance you will eliminate. Eliminate to form a, yes, you will eliminate to form a diene, which will be the focus of next chapter. Base, heat, water. Okay. Consider the following alkene. How many constitutional isomers could be formed by treating NBS in light? Well, how many allylic hydrogens are there? We have one right here, and this guy will not be chiral, so one there. You have one right here, but this guy will be chiral. So I'm going to go with 3, but I could be misreading constitutional isomers. No, 3. There we go. Draw all possible constitutional isomers. Ugh, okay. Okay, I'm gonna copy this down. Oh, I'm an idiot for different things. Constitutional. Okay. So we could add to there bromine. We could add to there bromine. But because of how it adds and conjugation can occur, if I'm adding, if I allow resonance to occur between when we add to this guy, this double bond could flip over to here. And so we could add the bromine there, and we have the double bond here. But that is basically the same structure. However, if I'm adding to the primary position and I allow resonance to occur, I can add to here, and suddenly, I can add to here, and suddenly we get a different product. Right? Oh, come on. Oh, my God. Okay. I don't know what I will be right back. Oh boy, because I closed out on the Alex and now suddenly it crashed out on me. Yeah. I'm not editing this. Sorry. It's going to be what it's going to be. Unfortunately. It should take me more than a few seconds to get that going again. Preview. We were at number. We'll do that one again. We'll do that one again, but stupid Alex, honestly. Nope, no, that's not it. Okay, there we go. Let's go back and do this one again. Okay. Oh, this one's only going to get... There's only 2 relics. Yeah. Now, the idea here... I'm going to draw this again. The idea here is that NBS only adds to the allelic position. But because of resonance... and you can get an extra spot. So I could add to this position, or I could add to this position, but that is the same isomer. So that doesn't count as a unique product. However, because of conjugation, when I make a radical, I can conjugate to here, and suddenly this is the allelic position. And so, not only do you have to count unique allelic positions, but any unique allelic positions that could be formed through conjugation. So, this guy, I could conjugate it that way or conjugate it this way, but either way, because of symmetry, you only get one unique position from the conjugation. Okay, HBr. So we're doing a radical mechanism. HBr, if we did a non-radical mechanism, would be Markovnikov, which, remember, Markovnikov means the guy with the most hydrogens gains the hydrogen. So a non-radical mechanism. So that means hydrogen would be adding to the secondary position. Bromine's going to add to the tertiary position. Because we are doing it radical, the bromine adds first, and then the hydrogen adds second. And so it goes anti-Markovnikov. How do I know it's a radical? The ROOR, that peroxide, makes this a radical. Peroxide makes it a radical. So it goes anti-Markovnikov. The H is added to here. The bromine is added to there. So here's another example of that exact same problem. Drawing the alkene. Say they're just reacting this alkene with HBr. So it's going to add Markovnikov fashion. The H adds to here, the bromine adds to there. And then you recognize, okay, what about in the presence of peroxide? So it's just the opposite. Anti-Markovnikov, where it's all about, Markovnikov is just about the order of addition that we are going to get. Draw the major product. I don't think they care about stereochemistry. No, they do not. So, recognize peroxide versus non-peroxide, radical versus non-radical mechanism. If you can recognize that difference, that's all it is. It's the same thing. Then what reagents would be needed to convert this guy into that guy? 1,2-dibromo ethyl cyclohexane. So the tricky, we want to add 2 bromines. Okay? 2 bromines. Usually the easiest way to do that is with Br2 over a double bond. Let's try another one. way too easy for the last problem. How would we make? How did we add that? Is it Markovnikov addition or anti-Markovnikov? We've added an H here and a BR there. It looks like it's Markovnikov addition. So we're going to just HBR. Try another one. Finally, okay. We're just getting rid of the double bonds altogether. We're not adding any length. Easiest way is hydrogen. So these don't seem to be radical mechanisms. They're just a reminder, what else can we do? Okay, we're adding PRBR. Same thing. Same thing as the first one. We're doing a hexene to a dibromohexane. So, as I said, that is this homework. Do try these problems. Do try these problems because some of these problems will come up on the test. Some of these will come up on the test, so make sure you kind of get a grasp on how the system likes you to enter the problems. So you know you can do that again on the test. Have a good day. I will see you on Monday, assuming the storm lets up and we don't get frozen out for another week.